So after looking at the homogeneous representation of points and lines, we'll now look at the representation of conics in the projective's 2D space. A conic is actually a curve described by a second degree polynomial equation in the plane on the Cartesian coordinates. And in Euclidean geometry, conics are of three main types, namely the hyperbola, the ellipse, as well as the parabola. And we'll see in the next slide that how these three different types of conics are generated from geometry. And these three types of conics arises as conic sections generated by planes differing from or of differing orientation. We'll see in the next slide that this is in fact the intersection of planes of different orientation that intersects two inverted cones. And note that besides these three different types of conics, there are also degenerate conics, which we'll define later. So here's the illustration of how the three main types of conics arises from geometry. The first type, which is parabola, it occurs when a plane intersects the two inverted conics at the location or at an orientation such that the tangent to this plane is aligned with the axis, with the side axis or tilted axis of the two inverted conics over here. So in this case here, the intersection of the plane with the two inverted conics, which is given by this curve over here, would define a parabola conic. And in the case where the tangent of the plane is aligned with the base of the, or parallel with the base of the inverted cones, then this will give rise, the intersection will give rise to a circle. And if it is tilted at a certain angle, but it's still close to the tangent of the plane is still close to the alignment with the base of the circle, then this will give rise to the ellipse conics. And in the case where the tangent of the plane is aligned with the vertical axis, parallel with the vertical axis of the inverted cones, then the intersection of this plane with the inverted cones would give rise to the hyperbola. So now, having looked at the geometrical intuition behind how the three different types of conics are formed, let's go into the mathematical formulation of conics. So we all know that the equation of conics in inhomogeneous coordinates or Cartesian space coordinates is actually a 2-degree polynomial given by this particular equation here. So let us follow the concept behind the homogeneous conversion of a point, where we saw that a point x can be represented as homogeneous coordinate of x1, x2, and x3, where we simply replace x with x1 divided by x3 and x2 divided by x3 to get the homogeneous coordinates, and or to get the coordinates in the Cartesian space. So this is a conversion between homogeneous coordinates and the Cartesian coordinates that we are familiar with. And in this case here, we'll simply divide the homogeneous coordinates, the first two elements of the homogeneous coordinates, with the third coordinate over here. And we'll do the same here. We'll simply replace x over here with x1 divided by x3 and and y over here to be replaced by x2 divided by x3 to get this particular equation here. So here we'll replace this x and y over here. So since this guy here is equivalent to x and y, we'll simply use these two equations over here, two relation over here, to convert from Cartesian to homogeneous coordinate. So now the homogeneous representation of the equation of conics, we can see that it's parameterized by x1, x2, and x3 with the coefficients of a to f that remains intact here. Now we can rewrite the homogeneous form of the conics equation into a metric form, which is given by x transpose of c multiplied by x equals to 0, where x here is simply x1, x2, and x3, and c here would be in terms of this metric form over here. It's a 3 by 3 metric, and now we can say that C is a homogeneous representation of a conic. And here only the ratio of the metric elements are important. Multiplying C by a non-zero scalar has no effect. This is similar to the homogeneous representation of a line and the homogeneous representation of a point. We can see that because this equates to 0, multiplied by any k scalar value, it will always cancel out, and hence there's no effect on the conics equation here. The conics can be seen to have 5 degrees of freedom, which can be thought of as a ratio of A, B, C, D, E, and F. Since we said just now that multiplying the conics equation with a k here would have no effect. This means that it's only the ratio of these 6 values, the 6 parameters of the conics, that is important. And in this case here, what we say is that it's also equivalently that the 6 elements of the symmetric metric less 1 for the scale, which is given by k over here. And hence, it's 5 degrees of freedom. So each point on the conics xi, which we denote as xi, the coordinates are xi and yi, places one constraint on the conics coefficient given by this second degree polynomial equation over here. And what this means geometrically is that given a conics, for example, this ellipse over here, when we have one point that lies on this particular conics, this is going to give one of these constraints. And this particular constraint in terms of this polynomial equation can be rewritten in a metric form, or in a metric, or in a homogeneous linear equation form, as this particular case. So this is equivalent to a vector or dot product of a vector, which will give us 0 over here, where C, this vector C here, is the coefficients of the conics A, B, C, D, and E, represented as a 6 vector here. So since we have 6 unknowns inside inside this 6 vector over here, this guy here is a 6 vector, which is actually a 6 unknowns over here. Oh, what it means here is that in order to solve for the 6 unknown, where less 1 minus 1 for the scale, this means that we have looked at this earlier, that there's only 5 degrees of freedom that defines the conics of C over here. So what it means is that we only need 5 constraints. We only need a total of 5 constraints, or minimal number of 5 constraints in order for us to solve for the unknown conics. So geometrically, what this means is that in order to solve for these conics, we need to know 5 points on these conics in order to solve for the conics equation here, which is represented by C. And stacking this up together, we'll get a homogeneous linear equation where this guy here is equals to A, and which is a 5 by 6 metric, and C here is actually a 6 by 1 vector, and this would be equals to 0. Or what this means in linear algebra is that C here, the solution of C here, lies in the null space of the metric of A here. And once these 5 points are known, this means that this coefficient here, the metric of A here, would be all known, a known value. We can easily solve for the null space of A to get the solution of C, which represents the conic equation. We'll see in the later lecture that this can be easily solved by doing the SVD, the singular value decomposition of A, and to get the null space of A, which will be the solution of C here. And one interesting thing to note here is the tangent lines to the conics. This is also the intersection of a line with a conic, and this will give rise to a point when this line forms a tangent to the conics. We'll also see later in the degenerate cases that sometimes the line might also intersect at 2 points, or sometimes the line will not intersect. But in this case here, we'll look at the case where the line actually is a tangent line to the conics. And when this happens, this tangent line to the conics is actually intersecting at a point which we denote as x, given by this equation over here, L equals to Cx. Here's the proof in the algebraic sense. So the line L equals to Cx passes through x. This means which is denoted as in this figure over here. This means that this line is actually a tangent line to the conic C, since there's only a unique point of intersection here at x. Since L transpose x equals to x transpose Cx equals to 0. So L transpose x is what we have learned earlier. When the point x lies on the line L, then this L transpose x, or the duality x transpose L, is going to be equals to 0. So in this case here, we are using this L transpose x equals to 0. And we have also seen that all the points that lies in a conic is going to fulfill this incidence relation where x transpose C x equals to 0. So if the line has one contact point, which means that this line is actually the tangent line to the conic, then it is a tangent and we are done. And we can see that in this case here, the L here and L here that fulfills this, since there's only one point of contact, which is a tangent line, then L here we can rewrite this L transpose equals to X transpose of C, which also implies that L is equals to C of X here. Hence, we have proven that the tangent line intersects the conic at L equals to Cx. Now, the conic that we have defined so far, it should be properly termed as a point conic, as it is uniquely defined by a equation on points. This is because the second degree polynomial that we look at, it's defining a point on a conic, and we saw earlier that 5 of these points that lie on the conic uniquely defines the conic. And there is also a dual to the conic, as in the dual of a line. So previously, in the previous slide, we saw that there is a point line duality given by X transpose L equals to L transpose X equals to 0. And this duality actually means that we can define a line with a point and interchange the point with a line as well. So what this means is that you can see that if I have many points over here, it actually can be used to represent a line. And if I have a line here, it can be at the same time used to represent these many points on the line. So here, there is also a duality between the line conic and the point conics. So a point conic is what we have defined earlier, which is uniquely defined by a set of 5 points or more than 5 points. So anything that is more than or equals to 5 points can be used to uniquely define this particular conic. We can also do the same with lines. So we can see that the conic can be uniquely defined with tangents of the line. So if I have many tangents of the using the line onto a conic, I can actually use it to uniquely define my conics. And this relation here is given by this equation over here, L transpose C star L equals to 0. We define C star over here to be the dual conics, which is defined by the line, or in other words, this is actually just the line conics. So we can see that the analogy would be our point conics, which is the equation that we saw earlier. It's X transpose C X equals to 0. So this means that the X here lies on the point, the point here lies on the conics, and in this case here, it means that the lines lies on the conics C star. So this case here is a C, and we have all the points of X. And this case here, the dual conics, we have all the lines denoted as L. And a dual conics also has 5 degrees of freedom. And what this means is that the conics can also be computed from 5 unique lines that define the conics. And for a non-singular symmetric metric C star, it's the dual conics denoted by C star over here is actually given by the inverse of the conics, of the point conics. So we can write C star equals to C inverse up to a certain scale. So the proof is here. Given a point x on the conic C, so let's say this is conic C, and given a point x over here that lies on the conic C, the tangent is, we have seen in the previous slide that the tangent is given by this equation here, L equals to C over X, C multiplied by X over here, and this implies that in this case, if C is invertible, X would be equals to C inverse L, and this means that we can rewrite this C inverse here with C star, which gives us this equation, this relation over here, which is the dual of this L equals to CX, the tangent line. So in this case here, we will have a point C star. This defines C star over here, where we have a point that defines by the line that is tangent to this C star over here. Hence this particular relation over here. Furthermore, since X satisfies this equation, the second degree polynomial equation that we have seen earlier, we obtain this relation by substituting the point with this equation, this particular relation over here, by substituting X with C inverse of L into X over here, into two sides of this quadratic equation over here, and simplifying this, since this is a transpose, C inverse L transpose will give us L transpose C inverse transpose over here, and what we can see here is that we will end up to have this equation over here, since C and C inverse is equals to identity, and C inverse transpose is equals to C inverse. Hence, we will get this particular relation over here. And as a result, we can see that this relation can be rewritten into L transpose C star L equals to 0 by simply saying that the dual conics is equals to the inverse of the conic. And geometrically, dual conics are also known as the conic envelopes, because I have said earlier that the dual line conics here is defined by all the tangent lines as compared to the point conic, which are defined by points on the conics. So 5 or more than or equals to 5 points can uniquely define this conic C. And here in the same case here, we have more than or equals to 5 lines, tangent lines to the conic. We can define the line conic C star. Now suppose that in addition to X, there's another point of intersection of the tangent line to the conics, which we denote as Y over here. And it follows that then Y transpose CY would be equals to 0, following the equation that we have seen of earlier of X transpose C, X equals to 0. And we know that since this particular point of Y must lie on the line L, then the intersection equation over here, the incidence equation over here, L transpose of Y must be also equals to 0, will hold. And we have also seen that there is another point of X earlier, that this must be the intersection of the tangent line and the conics. Therefore, the equation L equals to CX must also be true. And if we were to replace this particular L equals to CX in this equation over here, then we will get another relation of X transpose CY equals to L transpose Y equals to 0 over here. And interestingly, it follows that if all these relations holds true, that means that for the tangent line, there are actually 2 points that of intersection with the conics. Then it follows that this relation here must be true for all alpha. And what it simply means here is that X plus alpha Y is another point on the line. And what happens here is that X plus alpha Y, it actually means the line itself. And this simply means that I have 2 points X and Y, and any magnitude of this Y is going to denote any point on this particular line over here. And what this means is that if there's another point of Y in addition to X that lies on the intersection of the tangent line to the conic, then the whole line joining X and Y over here, the whole line here must lie on the conic. So what this means here is that the conic will no longer be an ellipse, hyperbola, or parabola shape, or even a circle shape. It means that the ellipse now, or this conics now, must also take a straight line. Therefore, the tangent line to this conics, which is also a straight line, would have all the points lying on the conic. And we say that this kind of conics is a degenerate conic. We will look at several cases of these degenerate conics. So we have seen algebraically that the conics degenerates when we say that any line that is tangent to the conic intersects the conic at every single point here in that is given by this equation here. So what this means is that given a line which is spanned by x and y, these 2 points over here, the conics is degenerate when it meets this particular tangent line at every point of the line that is spanned by x and y. And there are geometrically 3 cases where this can happen. In the first case, where x and y actually collapse to a singular point, this means that they are actually x is equals to y over here. And in this case, geometrically, what this means is that we will have the plane intersecting at the intersecting point of the peaks of the 2 cones over here. And in this case, we can see that this particular conics over here fulfills this equation for whichever x and y. And in the second case, we can see that it happens when the plane intersects exactly at the slanted axis of the inverted cones over here. And in this case, we can see that this intersection forms the line, this particular line over here. So this is the conic C over here. And any points, we can see very clearly from this illustration over here that any points on this line will still lie on this particular conic itself, because the conic itself is a line. And in the third case, the conics would be intersecting the 2 inverted cones, or the plane will be intersecting the 2 inverted cones in this manner over here, which it forms 2 straight lines over here. And in this case, whatever lines or whatever points that lies on either one of these 2 straight lines would also fulfill this particular equation over here. And they will all fulfill these 2 sets of equations, since we are saying that both x and y now of the tangent line, that it lies on the tangent line, as well as it must lie on the conics itself. We'll see that in order for this to happen, the rank of C must be less than 3. So I have mentioned earlier in the previous slide that if the metric is not full rank, then the conic is termed as degenerate. What this means is that the rank of C here must be lesser than 3, because C is actually a 3 by 3 square matrix, and anything the rank lesser than 3, this means that the metric is not full rank. And the degenerate conics that will include 2 lines and a repeated line of rank 2 and rank 1. We will look at these 2 cases or of the example. So in the first case where we are looking at here is that the conics is consists of 2 lines, and we'll see that it actually forms a rank 2 conic. And in this case, this conic can be formed by 2 lines, which I denote as L and M over here, and taking L multiplied by M transpose, this is the dot product, and plus the transpose of this dot product, we'll see that we'll get a rank 2 conics over here. And indeed, after putting into this particular equation over here, which is the conic equation that we have seen earlier, that from the 2 sets of equations over here, the 2 summation terms over here, multiplying it by x and x transpose and x over here, and we can see that this indeed gives us 0. And since from this particular equation here, which is the conic equation that we have seen earlier, that it actually reveals the 2 lines where the first term here, the dot product of x and L, denotes the first line equation of L, which is the line and the point that is lying on the line, as well as the second term here, which is the dot product of M transpose and X over here, where M is my second line and X is the point that lies on the line. So we can see that from this particular formulation here, it actually reveals two line equations over here. And hence, the degenerate conic in this case, where the rank is equals to 2, it's actually two lines which is represented geometrically from this using this particular figure over here. And in the second case, we can see that if the rank of the matrix is equals to 1, this means that the rank of the C matrix, the conic matrix equals to 1, then C is actually, the conic is actually a repeated line which overlaps each other, the same line, given by this case over here. So L transpose L plus L transpose is going to give me a repeated line, and with the rank of C here equals to 1. And in this case, we can put the same equation over here into our conics equation to get this particular relationship, which is equals to 0 over here. And here it's not difficult to see that after putting it into this particular relationship over here, we can see that this actually consists of two terms, which is the dual of each other, which highlights the point line relationship over here. And hence, L here and the L over here would be the same repeated line with rank of 1 forming the conics. So there also exists degenerate dual conics or dual line conics that includes 2 points of rank 2 and a repeated point of rank 1, as we have seen in the first case of the illustrations of the geometric illustrations of the degenerate conics earlier. And in this case here, an example would be the line conics C star equals to x y transpose plus y x transpose. So this is of rank 2, which consists of 2 points over here that is formed in this way. So the reason why it has to be formed in this way, because C is actually a symmetrical square matrix. So the way that it's formed in this way, it will ensure that C, the resulting C, is a valid conics, and it will also ensure that it has a rank 2. And this dual conics consists of lines passing through either of the 2 points, x or y. So what this means is that it will form something like this, where I have x and y over here, and this point would be made up of all these lines that is intersecting on the point over here. And similar formulation can also be done for the rank 1 line conics of the repeated points. So I won't go into the proof, or I won't go to show that this is indeed the set of points, because as I mentioned earlier, that the duality principle means that as long as I've shown it for the points conics, the same relation should also hold for the dual line conics over here. And note that in this case here, C star, which is my dual conics, the inverse of this is not equals to C. As what we have mentioned earlier, that if the rank of C is full rank, which is equals to 3, then C star would be equals to C inverse. But in this case, since the rank of C is not equals to 3, then this relation doesn't hold anymore. Now, after looking at the definitions of points, lines, and conics in the homogeneous coordinate space and in the 2D projective space, let's look at how these entities can be transformed in the 2D projective space. So 2D projective geometry, as I mentioned, is actually a study of the properties of the projective plane that are invariant under group transformation known as projective. So as I've illustrated earlier on that in this case here, the 2D projective geometry can be seen as the ray forming on projecting onto each one of these plane to form a line, or it could be the plane that is intersecting on the on these individual planes of k equals to 1, k equals to 2, or k can actually be any real number here, the intersection here, to form a line and a conics, etc. So in this case here, when we are studying the 2D projective geometry, we are studying how this transformation of these planes that intersects the line, the plane, or the inverted cones can result in the invariance or certain invariant property after the transformation. And specifically, a projectivity needs to be an invertible mapping, which we denote as H from P2 to P2 itself. So this means that I'm mapping any input point or input entity in the 2D projective space. It could be a point, line, or conics, and the mapping should also be mapped into a projective 2D space denoted by H. And this linear mapping simply means that if I have a point, I denote this H as a mapping, it should be able to rewrite it into this form where it becomes a linear mapping. And it should also be invertible. This implies that I should be able to recover x prime from the inverse of H multiplied by x over here. And this means that the mapping from one space, projective space, to another would be denoted as H, and the inverse of this would bring me back from the other space back to the original space. So a projectivity is also called a collineation or a projective transformation or simply a homography. The theorem of projective space is that, as I mentioned in the previous slide, is that given a mapping H, it actually maps an entity from a 2D projective space into another 2D projective space. And this mapping is a projectivity if and only if there exists a non-singular 3x3 matrix H here, which we denote as capital H over here, such that any point in the 2D projective space represented by a vector is true that the mapping follows this particular function over here. So in this case, I would have mapped it into x prime given by h multiplied by x. And both of x and x prime must be in the 2D projective space. And as well as h here must also be an invertible entity. Well, we'll skip the full proof. So the partial proof begins with let x1 and x2 and x3 lie on a line. So these three are lying on a line, x1, x2, and x3. Thus, this equation of the line point incidence relation holds true, where the dot product of the line and the points will be equals to 0 for 1, 2, and 3. And let H be a non-singular 3x3 matrix. So we can verify that after this mapping with H, as I have mentioned in the very beginning of the lecture, that despite that the geometrical properties of many shapes and geometry structures change when it undergoes projective transformation, the straightness of it will not be changed. So what this means is that if I were to map these 3 points on using this homography of H, then it would be transformed from a P2 space to another P2 space. But after the transformation, these 3 points should also appear collinear to each other. We can easily verify this by doing this. So a projective transformation of L is given by this guy over here, and a projective transformation of X is given by this guy over here. So in this case, I'm mapping the line independently from the points, and we can see that by putting both of them together, so this will end up to have L prime, which is this guy over here, L prime after the mapping, L to L prime, and this H xi would be my points of xi prime over here, and this would be xi over here. So putting them together in the coincidence relation, I will still get 0 because H inverse and H cancels out. What this means is that as a result, after the transformation, my L prime multiplied by the xi prime over here, it will still be equals to 0. What this means is that all the 3 points after the mapping, after the homography mapping, it will still be collinear to each other and it will still be lying on the line. Hence, the collinearity is preserved by the transformation. So what we want H to follow would be this. We want to find a H such that it's capable of mapping P2 space to P2 space where the collinearity is preserved and it's a linear mapping which is invertible. Following the principles or following the rules that we have laid out earlier for the projective transformation H, we now define the planar projective transformation in this metric form. Let's denote the P2 space, the final P2 space as x of x prime over here, as x1 prime, x2 prime, and x3 prime over here. And H here would be a 3x3 matrix that it's capable of doing linear projection or linear transformation of my original point x in the P2 space as well, and it will map this P2 space into another P2 space of x prime over here. Or simply we'll write this linear mapping relation as x prime equals to h multiplied by x. And here's some properties of H. It has to be a non-singular 3x3 matrix because, as mentioned before, H needs to be able to be inverted, and hence it has to be a non-singular matrix for this relation to hold true. It also has to be a homogeneous matrix since only the ratio of the matrix of the elements is significant, and it has to be 8 degrees of freedom. We'll see later on why it has to be 8 degrees of freedom among the 9 elements of H when we learn about the robust estimation of homography in the later lecture. Now, geometrically, what the transformation, what the homography transformation of projective transformation means is that we are actually trying to find a linear mapping such that, as we have mentioned, that x or any point it's represented by the intersection of the ray with the plane. So what we are trying to do here with the linear mapping is that instead of planes that are parallel to each other, which we have denoted using our homogeneous coordinates of x, y, and k, or kx, ky, and k over here, we say that by varying this particular ray over here is intersected by all the planes that are parallel to each other at a different interval, different k interval. So in this case here, it represents the same point. But a linear mapping, a homogeneous linear mapping simply means that I want to find, after I have transformed this plane into another plane, which is not parallel to this particular plane over here, by considering the same line, the same ray that intersects these two planes here, the relation between these 2 points, which I call x prime and x over here, would be related by a homography, which can be written as x prime equals to h multiplied by x. And hence, the projective transformation of x prime equals to h multiplied by x can arise in perspective images. Some examples will be given here, and these are the unique cases where this particular transformation can be valid. It doesn't hold in all cases, but it has to be a transformation from planes to planes, because as what we have defined in the earlier slide is that what we're interested in would be the origin with a ray. I want to find the intersection of this particular ray with different planes and the relation between these 2 points here, for example, which is the intersection of the planes with this particular line over here, would be related by the homography equation. Hence, it has to be a point lying on a plane in order for this to be valid. And another part that it has to be valid would be it has to be a perspective images. What this means is that all these light rays, all these rays over here, it has to converge at a single point of convergence. We'll look at this in the future lecture in more detail, but here we'll study the properties of this homography on different geometrical structure. So we have seen earlier that if a point xi lies on a line, then the transform point xi prime would be equals to h multiplied by xi under a projective transformation. And this, after the projective transformation, these points over here, which originally lies on the line, so all these points which I denote generally as xi that lies on the line L, it would be still lying on a line after the transformation, which I denote as L prime over here, and these points over here would be xi prime after the homography or the projective transformation. And the transformation of the point would be given by x prime equals to h multiplied by xi, and the projection of the projective transformation of the line would be given by this guy over here, in order for the incidence of the points on the lines to be preserved, given by this equation over here. We can see that by plugging in these two, the h over here will cancel out and it will be equals to 0. Hence, it will give us the incidence relation, which means that collinearity is preserved after this particular mapping over here. Hence, we can write the point transformation, given that if the point transformation is given by x prime equals to h multiplied by x, then the line transform will be given by L prime equals to h inverse transpose multiplied by L, or the transpose of this relation, which is given by this equation over here. And now let's look at how the linear mapping or the point projective transformation affects a conic. So under the same projective transformation of a point given by x prime equals to h multiplied by x over here, the conic transformation under this homography mapping would be given by this relation over here. C prime would be equals to h inverse transpose multiplied by c multiplied by h inverse. And under the projective transformation of x prime equals to hx, a dual conic point c star will transform to c star prime equals to h c star multiplied by h transpose. So this here is important to note that in this case here, c star would be equals to the inverse of c, where the rank of c is actually equals to full rank. This means that we are looking at the conics which is not degenerate. So here's the proof of the transformation of the conics and the dual conics. Under a point transformation given by x prime equals to hx, the following the equation of the conics, we have x transpose c of x, and this would be equals to x prime transpose multiplied by h inverse transpose, which is given by this guy over here. So what this means is that I'm actually substituting x with the inverse of h multiplied by h prime over here. So I'm substituting this guy here into this equation. Hence I get h inverse x prime transpose c h inverse x prime over here, which is given by here. And the transpose of this guy here would be simply equals to x prime transpose multiplied by h inverse transpose, which is given by this term over here. And further evaluating this expression over here, we'll get this final expression over here, and which is in the quadratic form of x prime transpose c prime x prime with and from this particular equation here and this relation over here, we can easily see that c prime after the transformation equals to this expression over here, which means that the transformation, the linear mapping of c would be given by this equation into c prime would be given by this equation. By the way, there's no inverse over here. Now, after looking at the definition of the homography, which defines the projective transformations of point, lines, and conics in the projective space, let's look at the hierarchy of transformation. And the first level of the in the hierarchy of transformation is what we call isometries. So isometries are transformation of the plane in the R2 space that preserve Euclidean distance. What this means is that in this case here, we are looking at the ray and the intersection of this with the plane over here, and we say that the linear projective transformation is which denote by H is actually geometrically trying to transform this plane into another orientation at another location. So in the case where they are evenly spaced out and parallel to each other, then in the homogeneous coordinates, they actually means the same point. So h over here is trying to relate h, x, and x prime, where these two planes are not parallel to each other. And there are special cases of h over here, which defines certain transformation geometrically of these two planes over here, such that it preserves the Euclidean distance. And in this case here, since h is a 3 by 3 matrix, which we say that it has 8 degrees of freedom, when all the 9 entries are free to move, or there's no constraints on the 9 entries in this particular H matrix except for the scale, hence there's 8 degrees of freedom, then there's generally no constraint between these two planes. But in the case where if H over here is a linear mapping that is defined by this 3 by 3 matrix over here, where we simply say that the first three or the first four elements is given by this equation over here, and the last one is given by tx, ty, and 1 over here, then this would be preserving the Euclidean distance. This equivalent to the isometry transformation, where this guy over here is a 2D rotation transformation, and this guy over here is a 2D translation. So what happens here is that suppose that I have a point in xy, and I'm rotating this by a angle of into xy, x prime and y prime. I'm rotating it with respect to angle of theta. Then this guy here would be the rotation matrix, or which is scaled, or which is has a symmetry element over here, which is given by epsilon. We'll see in the next slide what this actually means. And but assuming that epsilon is equals to 1, then this would be a rotation matrix that maps this particular point over here in the xy original xy axis into the new x and y prime axis over here after the transformation. And in this case here, the rotation would be where it's anchored upon the origin. And in the case where the origin actually moves, what this means is that I have the original axis of x and y, and in the case where I have rotated via a certain amount over here, so theta, and then I'm also translating with respect to this original xy axis by an amount of tx, ty, and 1. Then there's a translation over here which is given by this guy over here. And in this case, what I'm interested in looking at is that given a point which is originally x and y in the original axis over here, I want to find out what is the new coordinate of this in the new coordinate frames over here. And this is given by isometry transformation. And we can see that after the transformation, this axis over here, according to this axis or with respect to the previous axis over here, the Euclidean distance between any 2 points. So any 2 points over here, let's say if I have 2 points over here, and in the first case, they are before the transformation, both are expressed with respect to the original axis of x and y. Then we can see that the distance here is preserved. Even after the transformation, it will be now with respect to x prime and y prime over here. But the distance between these 2 points will still remain as d. Hence, it's preserving the Euclidean distance in this case here. So if epsilon equals to 1, then isometry is known as orientation preserving, and it's a Euclidean transformation. The rotation matrix and the translation vector that I have mentioned, we'll talk about this in more detail. I'll show more detail and derivations in the 3D space when we talk about 3D projective geometry in the next lecture. And if epsilon equals to -1, then the isometry reverses orientation. Hence, it becomes an reflection. What this means is that instead of just orienting it according to this way, so in this case, it would be the translation as well as a rotation of the angle into x prime and y prime over here. And the original axis would be x and y. So a point here that I'm interested in would be denoted in the new frame. It would be in this particular frame over here. But when epsilon equals to 1, when epsilon equals to -1, then what I will be doing is that I'm actually reflecting this axis into here. So now this point must be with respect to x prime prime and y prime prime over here. And we can see that regardless of how this particular point or how any 2 points undergoes the isometric transformation, the distance between the 2 points will always be preserved. This means that the length will be preserved, as well as any 3 points. If I form an angle over here, is also going to be preserved after the transformation, and the area is also going to be preserved. So the second hierarchy of transformations that we are looking at is the similarity transformation. It's an isometry composed of isotropic scaling. So in this case, in addition to the rotation matrix and the translation vector, we have an additional scale. This means that I'm scaling up or down the scale of the all the points in the space, or the lines and the conics in the space. And we represent where this scalar S here represents an isotropic scaling. The isotropic means that it's going to scale equally in both the x and y axis. And a similarity transform is also known as the equiform transformation because it preserves the shape. So in other words, after the transformation, for example, if I have a square denoted by that's formed by these 4 points over here, after the transformation, let's say the rotation equals to identity and the translation equals to 2 in the x direction, tx equals to 2. So I'm moving it in this way. Let's say I'm moving it in this way. Then s here equals to 1, or s here equals to 2, for example. So what this means that I'm scaling this up into 2 times the scale. So after the transformation of 2 steps into the x-axis, so this would be the end result, and the transformation here would be simply given by the similarity transform or equiform transformation. And we can see that after this transformation, because straight lines has to be preserved, the mapping of straight line has to be preserved, and the shape of this will be similarly preserved. H here has 4 degrees of freedom, 3 isometry plus 1 scale, in comparison to the previous isometry transformation that we have seen, where there's only 3 degrees of freedom in that case. So in addition to the preservation of shapes, the angle, the ratio of 2 lengths, and the ratio of areas are also preserved in this similarity transform. The third level of the transformation is what we know as affinity, and affinity transformation is a non-singular linear transformation followed by a translation, and it's represented using a 3x3 matrix over here. So in this case, there's no more notion of rotation matrix, where there's no more notion of the orientation around the z-axis in this case over here. So here the 4 elements over here are free numbers. That means that they can take any numbers, and where this A over here, the A matrix over here, the 4 number has to form a 2x2 non-singular matrix, because at the end of the day, H over here has to be invertible, and altogether HA over here would have 6 degrees of freedom and can be computed from 3 points correspondences. And because each point, we'll see in the lecture when we talk about homography, that each point correspondence would give us 2 degrees of freedom. Hence, 3 points would be sufficient for us to compute these 6 degrees of freedom. But we'll defer this to lecture 4 when we look at the homography estimation. And the invariants in this case are the parallel lines, the ratio of the length of parallel line segments, as well as the ratio of areas. We can see that the affine matrix A can always be decomposed into 4 components here, denoted by R theta, R minus phi, and D, as well as R phi over here. And in this case, r theta and r phi are rotations by theta and phi respectively, and D is a diagonal matrix, which we can see that this decomposition actually follows directly from the singular value decomposition, which is given by this guy over here. This is a definition of singular value decomposition. It can always be any matrix, any square matrix can always be decomposed into or factorized into the left orthogonal matrix and the right orthogonal matrix, as well as the diagonal matrix that contains all the singular values, which is also the eigenvalues of the matrix of A over here. And we can see that from this factorization, since U and V are octagonal matrices, what it means is that we can simply take U and D and V transpose apart. So we can write U here and then D and V transpose over here. And this, we can see that the product of these two terms over here will still give us A, because it's the singular value decomposition. Since the V matrix over here is a octagonal matrix, this means that the transpose of V is also equals to the inverse of V, and hence the V transpose multiplied by V over here would give us an identity. So by inserting these two terms over here, it wouldn't affect the end results of this multiplication, and hence as a result we can group U and V transpose together and call it R of theta. And this is since U and V are octagonal matrix, the multiplication of two octagonal matrices is still a octagonal matrix, which is a rotation matrix in this sense over here. And in this case here, we would have VD multiplied by V transpose, which can be written in this way over here. Since V transpose equals to V inverse, hence we can write that this V over here is R of minus theta, is a rotation matrix, and V transpose here would be the inverse of it, which is simply given by the negative of the angle in the rotation matrix. So we have seen that the affinity transformation matrix denoted as A over here can be decomposed into four terms using the singular value decomposition. And these four terms consist of rotation matrices as well as a diagonal matrix, which consists of the eigenvalues. What it simply means here is that if I have a original axis over here, which is denoted by this particular diagram over here, after the transformation, the affine transformation of applying A on it, this is what it's going to become. It's going to get skewed in the two directions over here, as well as it's going to be rotated at a certain angle over here. And what this essentially means after the decomposition here, since A is a 2 by 2 matrix which represents the first four elements of the upper left matrix of HA, and what this simply means is that I would have apply a rotation first that rotates the original axis by a certain amount over here. So in this case, it's rotated by 5 degrees over here into the new axis over here. And then the second term over here, I'm multiplying it by a diagonal matrix, which is simply equivalent to skewing or scaling the axis in an individual value that is given by the diagonal value over here. So in this case, it could be the case where I'm scaling it with lambda 1 and lambda 2. This means that D is actually equals to lambda 1 and lambda 2 over here. So a multiplication with this simply means that I'm multiplying the first component of X with lambda 1 and the second component of X with lambda 2. Hence, I'm actually scaling it, or I'm skewing it in the stretching it in the with the components of lambda 1 and lambda 2 here. Then finally, we will be multiplying this with two rotation matrices after the scaling with lambda 1 and lambda 2. We are going to multiply it with minus 5, a rotation matrix of minus 5. What this means is that I'm going to actually rotate this guy back into the upright axis. because I previously multiply this phi over here. Now I'm going to undo this rotation, but after this I'm also going to apply a final rotation of theta to this, and this means that from the upright axis I'm going to now apply a theta rotation, and this would be the final configuration after applying A over here. Now, the highest form of projective transformation in the hierarchy of the transformation is the projective transformation itself, and this is also known as homography. Is generally denoted as a non-singular linear transformation of homogeneous coordinates, as what we have mentioned earlier. So this would be H here, which is 3 by 3 matrix with 8 degrees of freedom that we have seen earlier. So where the scale doesn't matter, but now we have all the numbers, the 3 by 3, which is 9 numbers in this H matrix that can be filled out with any numbers. So here V can be also 0, and it doesn't matter, it can be any number. Here, as I mentioned, that HP here has 9 elements, but the ratio is only the ratio is significant. Hence, it has a 8 degrees of freedom over here. Note that it's always not possible to scale the matrix such that V is unity, since this particular component over here could be 0. So it is not possible to actually scale the homography or the HP matrix into 0, 0, 1 to become the similarity transformation or the affine transformation, etc. And a projective transformation between the two planes can be computed from 4-point correspondences with no 3 points collinear on either plane. So we'll look at this in more detail when we talk about the homography estimation in lecture 4. But an intuition here is that the HP here has 8 degrees of freedom, and as I've mentioned, each point correspondence will give 2 degrees of freedom constraint. So altogether, we will need 4 correspondences to find this general projective transformation. And another point here is that it's not possible to distinguish between orientation preserving and orientation reversing projectivities in the 2D projectivity space, because all the numbers, or at least there's 8 degrees of freedom where all the numbers are free, and the invariance here is the order of contact, the tangency, and the cross ratio, which we will talk about it later. Here's a summary on the hierarchy of transformation. So far we look at the Euclidean transformation, the similarity transformation, affine transformation, and the projective transformation, and the invariant properties are given here. Now it can also be shown that the projective transformation can be decomposed into a chain of transformation given by HS multiplied by HA multiplied by HP, where this guy here is the similarity transform, this guy here is the affine transform, and this guy over here is the projective transformation, which is denoted by these 3 cases over here. And in this case here, this projective transformation here, it has to take a special form of identity and 0, but the combination of all these 3 would give us a general projective transformation denoted by H over here. This is the highest level of the hierarchy in the hierarchy of transformation, which we have seen in the previous slide. A here is a non-singular matrix given by, which can be further given by this particular expression over here. It's where S here is the scale, R is the rotation matrix, and K is an upper triangular matrix plus T is a translation vector, and V is a 3 by 1 vector over here. And this decomposition is valid provided that V is not equals to 0, that this guy here is not equals to 0, and is unique if S is chosen to be positive. We'll see more of this, how this decomposition preserve geometric properties of the line at infinity and the circular points when we talk about circular points and absolute conics in lecture 3. Now let's move on to talk about the projective geometry in 1D space. So we have seen earlier that in the 2D space, a point is actually a ray in the 2D space that intersects a plane. And we saw the homogeneous representation that this is going to be intersection at all the parallel planes that represents the same particular point. And in the case of the line, it would be the intersection of a plane with the line with the plane over here that forms all these lines and the representation in the homogeneous coordinate. So here it somehow gives us an intuition that from a point it becomes a ray when we represent it in homogeneous coordinates, and from a line it becomes a plane in homogeneous coordinates. So what this means is that in the 1D space, we can also think of it this way, that all the points are actually living on a line, because in the 2D space, we're looking at the intersections of the geometric entity with a plane, all the entities that is living on a plane. So in the projective 1 space, we will be looking at all the entities that's living on a line. And in this case here, it would be only possible for points to live on this particular line, and also the line itself. Hence, the projective geometry in 1D would define points and lines. And we'll do the same here, except for in 1D space, in the 1D projective space, instead of a 3-vector, we now have a 2-vector to represent the points as a homogeneous coordinates. So we will have x1 and x2 here. And when x2 equals to 0, that means that this is an ideal point on the line. It's a point at infinity on the 1D space. And similar to the 2D case, a projective transformation of a point x is represented by a 2x2 homogeneous matrix over here, where we denote it as x bar multiplied by this, and it will transform it into x prime. So what this means is that we are looking at the how this point transform from that lives in a certain line over here, how it transform from this particular line onto the other line, where it becomes x bar and x bar prime over here, given by the projective transformation of H 2x2 matrix. H 2x2 has 4 elements, and it's where the scale actually doesn't matter. So there's a total of 3 degrees of freedom, and hence this H over here can be computed from 3 points. So in the case of the 2D projective geometry, we say that the straightness of the transformation of a geometric entity has to be preserved after a projective transformation in the 2D space. And in the 1D space, after the geometric transformation or the projective transformation, the property that must remain would be the cross ratio. And the cross ratio is defined as the basic projective invariant of the 1D projective space, and is defined by this particular equation here. So given 4 point in the 1D projective space that is defined by x bar I over here, so assuming that I have x bar 1, x bar 2, and x bar 3, and x bar 4 over here, the cross ratio can be computed as the determinant of the product of the 2 points over here and the metric multiplication of the 2 points over here. So this guy over here represents the determinant, which can be computed using the determinant equation. So it will be just the cross product of the cross multiplication of these 2 elements minus the cross multiplication of these 2 elements over here. So in this case, after we compute this will be a number that is an entry over here multiplied by another number, and the whole thing would end up to be also a number, a scalar number. So this would be the cross ratio, and it should be preserved under projective transformation. What this means is that if these 4 points over here undergoes an projective transformation of H2 by 2 over here, the 4 points after the projective transformation, the cross ratio that is computed from x1 bar prime, x2 bar prime, x3 bar prime, and x4 bar prime should be the same number. And geometrically, this is how it means over here, the illustration. So in the 2D space, we can see that the ray, or to represent a point, is a ray intersecting with a plane. But in the 1D projective space, it's actually a ray that intersects with a line over here. And the points are represented as a 2 by 1 vector over here. So in the case where it undergoes a certain projective transformation of 2 by 2 matrix, we're actually transforming this particular line into another line over here or another line over here. So here, in this case, after the transformation, the cross ratio after this transformation here should be equivalent. I'll leave it to you as an exercise to prove that this is true after the transformation. But basically, what you should do would be to simply substitute this guy here back into the cross ratio equation and show that the homography over here, the h2 by 2 over here, would cancel out each other, and hence the numbers would become the same. Now, there's also a duality of the points and lines in the projective 1D space, and we call this the concurrent lines that fulfills the cross ratio property. And the configuration of the concurrent line is dual to the collinear points on a line. And what this means is that if I have a set of points that are collinear lying on this line, then all these rays or all these lines that passes through each individual points over here and intersecting at a certain convergent point over here, and the intersection of these 4 lines with this line, the collinear, where the 4 intersection points is collinear to each other, would define the same cross ratio, and we call this set of lines the concurrent lines. And other properties of these concurrent lines would be any coplanar points denoted by xi over here. This means that all these, for example, these 4 points x1, x2, x3, x4, they are living on a plane, which is the plane of this PowerPoint slide over here. And once they all forms a line that converges at a certain converging center, projection center, which we denote as C over here, it will intersect any lines over here at 4 collinear points denoted as x bar 1 to x bar 4 here. And this would also fulfill the cross ratio property. It can be thought of the projection of the 2D space over here, which is lying of all these points lying on a plane into a 1D space here. And in particular, this line here would represent the one-dimensional image of the projection. The cross ratio of these 4 collinear points would be satisfied as well. So in summary, we have looked at how to explain the difference between Euclidean and projective geometry, and we have used homogeneous coordinates to represent points, lines, and conics in the projective space. Then we look at how to describe duality relation between lines and points, and conics and dual conics, and we also look at how to apply the hierarchy of transformation on point, lines, and conics, as well as we also look at the properties of a 1D projective geometry. Thank you.